Hello, my name is Chilukuri Mohan. I'm a professor at Syracuse University. I have a PhD in computer science from the State University of New York at Stony Brook, and I have been teaching at Syracuse University in the computer science program since 1988. The early part of my research, my PhD thesis, as well as for a number of years following that, I used to work in automated reasoning, in theorem proving, in logic, and areas which have a lot to do with the material covered in this course. I enjoy logic. That's something that I have really a great amount of fun doing, and there's lots of puzzles and things which I like to play with using logic and the tools that logic provides to us. The topic of this course involves the application of logic and formal methods in the context of computer science. In the process, we'll be first, of course, defining various logics, trying to understand what logics are all about and the distinctions between various logics. Some of the logics are rather simple, some of them are rather complex and are new to a lot of us, and we'll be wading through them. The most important thing is that in this course, we are not just using a mechanical approach to logic, but rather trying to understand the relationship between the models and the semantics and the meanings that we can attach to formulas and relating them to what we can do by symbol pushing, or in other words, by applying inference rules and carrying out proofs in mechanical manners. Eventually, of course, what we'd like to be able to do is to use mechanical theorem provers or mechanical reasoning procedures and automated reasoning procedures to help us make interesting and useful inferences about real systems and the behaviors of real systems. That is something that I hope that this work will in fact help. The other main area that I would be concerned about is the fact that in the current practice of software engineering, lots of software is designed and tends to crash for no reason at all, or behave in unusual ways, or sometimes it might be open to exploitation, which will lead to exploitation of vulnerabilities in the software, so that those who have evil intents can perhaps take advantage of the fact that you're using a particular software and get into your data and so on. So there are a number of concerns that we have in the areas of cybersecurity, cyber assurance, and privacy, and so on. And these cannot easily be addressed by just testing software on various data, checking that it works well, and therefore putting it out on the market. Instead, the careful use of formal methods and logic can in fact allow us to prevent a number of problems before they occur. So it is very important for today's practitioners, today's computer scientists, to understand how logic can be applied and how it can be used effectively in order to prove properties about computer programs. Some of them are positive properties. Computer programs need to be able to do certain things we want them to do. And it also is necessary to ensure that they don't do something that we don't want them to do. In particular, issues such as, for instance, data safety and not crashing and not getting into deadlocked states. These are things that we worry about. These are relevant not just for software, but also for hardware and for large systems in which there are a number of different components. Some of them are hardware components and some of them are software components. Very often we have to prove the properties of each of these and put them together in a careful manner so that we can in fact be assured that they will work without crashing at unexpected times or in unexpected places. This is what the course is centrally concerned about, and there are three broad divisions to this course. In the beginning, in the early part, for about 3 weeks, we'll be talking about traditional logics in general, then propositional logic, then first order predicate logic. Then in the next step, we'll be looking at the application of these logics for computer system verification, in particular program verification using a simple structured programming language construct. So trying to show how we can reason about the partial correctness and termination resulting in the total correctness of programs. We'll show how we can do this in a methodical manner, and where we have some guarantees about the performance of these programs. Then in the last part of the course, we'll be looking at more elaborate and unusual logics, including temporal and modal logics, which allow us to reason about systems whose behavior changes over time. For instance, systems might transition from one state to another state over time, and then we want to know what might happen in future, whether certain properties hold at all times, whether multiple different communicating entities do so in reasonable manner, and in case you have scenarios where multiple entities need to access the same resources, whether they can do so while nicely handling contention and not leading to large-scale systems crashes. Related to these temporal logics, there are other logics which are also modal logics, which allow us to reason about the beliefs and knowledge and other properties of agents, as well as other aspects of computer systems, including software systems. So this is what we cover, and some of this material would be familiar to those who have had prior exposure to logic. However, even for those students, it is very important to get some practice. We very often learn by doing, and it is easy to look at completed proofs and see that they work and they work correctly. But in addition to that, we need to be able to, in order to succeed in this course, as well as in its applications in future life, it is necessary to do a lot of practice with a lot of proofs and work with many examples and work them out and make sure that they are correct, and they're correct to your satisfaction. Usually in logic, if an answer is correct, you can see it. You can see it very clearly. And over time, we get used to the habit of developing shorthands and doing things rigorously enough to the point where sometimes we may not state things extremely formally, but we know that they can be stated, and we are capable of making a transition to a very formal statement, but perhaps we can carry out rigorous reasoning even in English, or even at a higher level of abstraction than some of the logic formulas that we use in this specific course. So logic is a very important tool in everybody's toolbox, and for computer scientists it is truly essential. And today, in the context of cybersecurity concerns, it is all the more imperative for every computer scientist to have a solid grasp of logic and be able to apply it and show that what he or she designs does in fact work as expected.